Hello and welcome to Lecture 3 of Advanced Topics in Quantum Information Theory. This lecture is on smoothing and optimizing the max relative entropy, and exactly what those two things mean and how they relate will become clear in just a moment. Let's begin by recalling the definition of the max relative entropy, which we introduced in the previous lecture. What this lecture is about, in a nutshell, is what happens when we minimize the max relative entropy in either argument over various choices of convex sets. Two particular senses or settings in which we're interested in minimizing the max relative entropy over convex sets of inputs are as follows, and these are the two concepts mentioned in the title of the lecture. First is smoothing. We assume that we're given ρ and q as arguments to the max relative entropy, as well as a positive real number epsilon, and we consider the infimum of the max relative entropy of xi with respect to q as we range over all density operators xi that are epsilon close to ρ, with respect to some notion of closeness that isn't specified on this slide. In the expression that you see here, the notion of xi being epsilon close to ρ is written as xi being contained in the set b sub epsilon of ρ, and the precise definition of this set depends on exactly what notion of closeness one might be interested in. We do assume that b sub epsilon of ρ is a convex set, and that is a property that we would naturally expect from a very wide range of notions of closeness. We'll come back to this shortly, and I'll mention a few common choices for how b sub epsilon of ρ is defined. Anyway, the quantity that we obtain is known as the smoothed max relative entropy of ρ with respect to q. The second way that we can minimize the max relative entropy over a convex set of arguments, naturally, is to optimize over the second argument rather than the first. Now, I'm not really sure what the most common or accepted terminology is for referring to these two arguments of the max relative entropy, or to the ordinary relative entropy for that matter, but I'm going to refer to the first argument as the actual state and to the second argument as the model. That's consistent with the basic idea that a relative entropy-like function describes a loss of efficiency when one plans for q, the model, but receives the actual state ρ instead. This is perhaps non-standard, I'm just choosing names for the sake of convenience. In any case, when we minimize the max relative entropy of ρ with respect to q, for q ranging over some convex set C, it's as if we're considering which choices of q in the set C incur the smallest possible losses of efficiency when serving as models for ρ. We're now going to look at these two optimizations separately, beginning with the first, the smoothed max relative entropy. Here again is the definition of the smoothed max relative entropy of ρ with respect to q, where b sub epsilon of ρ denotes the set of all density operators xi that are epsilon close to ρ with respect to some way of measuring closeness. You will in fact find that different authors make different choices for this set. One natural choice is to let b sub epsilon of ρ be the set of all density operators xi having trace distance at most epsilon from ρ. It is also very common that authors use a different definition based on the fidelity rather than the trace distance. For example, we might take b sub epsilon of ρ to be the set of all density operators whose squared fidelity with ρ is at least 1 minus epsilon. If we do choose b sub epsilon of ρ in this way, meaning in a way based on the fidelity, then we do gain one advantage, which is that our notion of smoothing will generally respect or get along well with extensions and purifications of states. Yet another common notion of smoothing takes b sub epsilon of ρ to include not only density operators, but also subnormalized density operators, meaning positive semi-definite operators with trace at most 1. This naturally requires that we define the max relative entropy a bit more generally, not requiring the first argument to be a density operator, but allowing subnormalized density operators. It's actually exactly the same definition as before, but we need to be a little bit careful when we're using it. Any facts concerning the max relative entropy that depend on the first argument having trace equal to 1 might then fail to hold. In this course, though, I'll stick with the requirement that the first argument of the max relative entropy is a density operator and will avoid smoothing to subnormalized states. It's just a bit simpler and more intuitive to keep everything normalized, at least in my opinion, although there is a small price to be paid in doing this. Specifically, we'll end up with slightly more complicated derivations on maybe 1 or 2 occasions when we're forced to normalize subnormalized states. Incidentally, in the third possible choice for b sub epsilon of rho that I've written here on the slide, you'll notice that the fidelity squared is at least 1 minus epsilon squared as opposed to 1 minus epsilon. This definition is equivalent to psi having so-called purified distance at most epsilon from rho. My aim in pointing this out is simply to mention that some authors adopt this definition. Naturally, you should always be sure to understand precisely which definition is being used by a given author. Now, obviously, the specific choice that one makes in defining the set b sub epsilon of rho will have an impact on the properties of the smooth max relative entropy and on bounds and relationships it has to other quantities, but in a qualitative sense, it really doesn't make too much of a difference so long as the associated notions of closeness are comparable. The basic idea is that the smooth max relative entropy reflects a tolerance for small errors, which we often have or would like to express when analyzing operationally defined notions. Without smoothing, the max relative entropy can sometimes, in certain settings, have unwanted hypersensitivities that smoothing eliminates. To better understand the smooth max relative entropy, it is helpful to consider a much more general setup in which the max relative entropy is minimized over an arbitrary closed and convex set C of actual states, meaning possible first arguments. As a shorthand notation, I've indicated that here by placing the set C as the first argument of the max relative entropy, and whenever we do this, it will be our assumption that we're minimizing over this set. Now, if we expand the definition of the max relative entropy, we find that the value obtained by this expression is equal to the logarithm of the optimal value of the optimization problem shown here. This might or might not be a semi-definite program. That depends on the properties of the set C. As we will see, however, it is possible to express this problem as a conic program for any choice of the set C, so long as it is a compact and convex set. In order to set this problem up as a conic program, let's focus for a moment on the convex set C. And just for the sake of generality, let's take C to be a subset of an arbitrary finite-dimensional real inner product space V. We may then form a closed and convex cone, which here is called L, by taking L to consist of all pairs, where the first argument, lambda, is any non-negative real number, and the second argument is lambda times u, for any vector u contained in the convex set C. It is clear from its specification that L is a cone, and it is not too hard to prove that L is closed, given that C is compact. Now, I did make a mistake in the first version of this lecture. I said that L is closed so long as C is closed, and that is incorrect. We need the compactness of C to draw this conclusion. It is the case, however, that because the set of density operators itself is compact, every closed set of density operators is also compact, so it doesn't make any difference in the particular case at hand, but it was an incorrect statement in general. By the way, I guarantee you that this will not be the last mistake I make in these lectures. Naturally, I try not to make mistakes, but they happen, and you should not hesitate to question what I'm saying if you think it is incorrect. Finally, the convexity of L can be verified as follows. Consider any 2 points in L, which here are distinguished by the subscripts 0 and 1, and take any convex combination of them. Averaging in the first coordinate indicates directly what the value of lambda has to be for the new point that results from taking the convex combination. And averaging in the second coordinate and dividing by lambda reveals what the vector u must be in the second coordinate. And we find that this vector u is a convex combination of u0 and u1, and it is therefore in C by the convexity of C. We really should also take the possibility that lambda equals 0 as a special case so that we don't divide by 0. But it is perhaps obviously a very easy special case to handle. Now, this is a very simple construction of a closed convex cone from any closed and convex set that can be used quite generally to express optimization problems over convex sets as conic programs. And it will be helpful, particularly when the time comes to try to understand the dual problems of the conic programs we formulate, to have an understanding of what the dual cone to L looks like. So let's do that now. By definition, it's the set of all vectors delta v for which the inner product with lambda u is non-negative for every non-negative lambda and every u in C. And by factoring out lambda, that's equivalent to delta being at least -1 times the inner product of v with u, again for every u in C. By defining a function psi sub c as the infimum of the inner product of its argument v with u taken over all u in C, we obtain perhaps the simplest expression of L star that we can hope for without knowing anything more specific about C, and that is that L star contains all pairs delta v for which delta is at least -1 times psi sub c of v. That characterization of L star will be useful in a moment, but let's get back to our optimization problem. Using the same idea of allowing a convex set to define a convex cone that we just saw, we'll define a cone K as follows. The first coordinate of K is lambda, and the second coordinate is lambda times xi, ranging over all non-negative lambda and all xi in C. So the first two coordinates play the same role that the two coordinates in the cone L play for whatever specific choice of a closed and convex set C of density operators we happen to be interested in. The third coordinate of K ranges over all non-negative real numbers eta, and the fourth coordinate ranges over all positive semi-definite operators P. Thus, K is essentially the Cartesian product of three closed and convex cones. The cone formed by the first two coordinates, which is just like L, the cone of non-negative real numbers in the third coordinate, and the cone of positive semi-definite operators in the fourth coordinate. And if we squeeze in the statement of the optimization problem we're interested in, you might see how it can be expressed as a conic program over K. We have a variable eta that will correspond to the objective function. We have a density operator xi that's drawn from C, and we have a positive semi-definite operator P that will be useful for expressing the operator inequality between xi and eta times q. To be precise, we can express our optimization problem as the primal problem of a conic program over the cone K, as is written here. The objective value is clearly eta, and the affine linear constraint in the problem enforces that lambda must equal 1, and that eta times q minus x minus y equals 0. Because y ranges over all positive semi-definite operators, this equality constraint is equivalent to eta times q minus x being positive semi-definite. And given that lambda must equal 1, we see that x must correspond to a density operator in C. All of this under the assumption that the tuple lambda x eta y is drawn from the cone K. Now let's take a look at the dual problem. We can begin by writing down the dual problem according to its definition. Obviously, we're going to need to simplify this problem statement in order to understand it better, and that's going to require that we compute the adjoint of phi and figure out what K star looks like. The adjoint of phi can simply be computed, or if you prefer, verified. The four coordinates of phi star applied to the pair mu z are mu, negative z, the inner product of q with z, and negative z again. If you are so inclined, you may wish to pause the video and verify that this function indeed satisfies the requirements of being the adjoint. Computing adjoints of linear functions like this becomes quite mechanical, but if you haven't practiced doing it a bit, it may not seem so obvious. Anyway, if we plug this expression into the dual constraint and perform the subtraction, we find that the dual constraint is that the tuple negative mu z, 1 minus the inner product of q with z, and z again, must be contained in the dual cone to K. Now, to understand the dual cone of K, we recall that K is essentially the Cartesian product of three closed and convex cones. The first cone corresponds to the first two coordinates, lambda and lambda times xi, and that's a particular instance of the closed and convex cone L that we discussed a few slides ago. The second closed and convex cone corresponds to the third coordinate eta, which ranges over all non-negative real numbers, and the third closed and convex cone corresponds to the fourth coordinate P, which ranges over all positive semi-definite operators. The dual cone to any Cartesian product of closed and convex cones is equal to the Cartesian product of the dual cones, so we obtain this expression of K star. The first two coordinates look just like the dual cone to L that we considered previously, with the function psi sub c being defined in exactly the same way that we saw before, while the third and fourth coordinates again range over all non-negative real numbers and all positive semi-definite operators respectively. And that's because the closed and convex cones corresponding to the non-negative real numbers and the positive semi-definite operators are self-dual cones. If we now reconcile this expression of k star with the dual constraint we obtained previously, we find that this dual constraint can alternatively be expressed as all three of the following constraints being met. First, it must be that mu is at most psi sub c of z. Second, the inner product of q with z must be at most 1. And third, z must be positive semi-definite. So, the problem can be expressed as you see here, and naturally we can simplify the objective function just a bit by computing the inner product, and so we obtain this. We can simplify this even further by observing that the maximum value that mu can take, subject to the constraint that mu is at most psi sub c of z, is simply psi sub c of z. And at this point we have something that looks quite nice, really. It's very simple and intuitive. Let's bring the primal problem back into the picture so that we can see the two problems side by side, as we always like to do with the primal and dual formulations of optimization problems. Notice that in the case that the set C contains a single density operator, rho let us say, we obtain exactly the semi-definite program for the max relative entropy of rho with respect to Q, as we would expect. Strong duality always holds for this conic program for every possible choice of a compact and convex set C. That follows from Slater's theorem, along with the observation that the dual is always strictly feasible. Now I should stress that the right way to verify this is not to look at the simplified statement of the dual problem written here, but to go back to the expression that refers to k star and to consider the relative interior of that cone. The primal is strictly feasible as well, so long as there exists a state psi in the relative interior of C, for which the max relative entropy with respect to Q is finite. We don't actually need strict feasibility in the primal to conclude that strong duality holds, but we do get it under this simple and, let us say, very typical assumption. That is, there's really no point in including choices of psi in C that result in infinite values. And so if we restrict C to those psi whose image is contained in the image of Q, then we will have strict primal feasibility, so long as restricting C in this way results in a non-empty set. This relies on the fact, by the way, that the only way that a convex set can have an empty relative interior is if the set itself is empty. For a quick example, let's look at the smoothed max relative entropy where the smoothing is done with respect to the trace norm. We will have more to say about the smoothed max relative entropy in the next lecture, but for now we'll just briefly consider it in light of the conic program formulation we just studied. Here's what the conic program looks like if we plug in b sub epsilon of rho in place of c. The effect that the smoothing has on the value is reflected in the dual by the function psi in the objective function. Without knowing more about rho, q, and epsilon, it's hard to say too much about this value. Smoothing can lead to a very significant decrease in the max relative entropy, but looking at the dual can, for instance, yield useful lower bounds on the smooth max relative entropy. Now let's switch gears a bit and consider what happens when we minimize the max relative entropy over a convex set, not in the first argument, but in the second. That is, let us consider minimizing over models rather than actual states. Using a similar shorthand notation to before, we may write the convex set C that we're minimizing over as an argument, with the understanding that this means that we take the infimum over all Q in this set. The value that we obtain is the logarithm of the optimal value of the conic program that you see here. The primal formulation is obtained by simply unwrapping the definition of the max relative entropy. It may look for a moment like we have introduced a quadratic constraint, given that eta is multiplied W. But if you think about the trick we used when we formulated the minimization over actual states as a conic program, you may see that the primal problem that we have here is also very easily cast as a conic program. To compute and simplify the dual to what we have here, one may go through a similar process to the one that we just went through when minimizing over actual states. I have done that offline, and if you feel that you could use some practice in computing and simplifying conic program dual problems, then I encourage you to do this with this one yourselves and check that your answer agrees with what's written here. It has a very similar nature to the dual problem we obtained before, but there are some differences. This time, instead of psi sub c, we have theta sub c, which is defined by a supremum rather than the infimum, but it does have the very direct relationship to psi sub c that you see expressed here. This function theta sub c is actually the much more famous sibling of psi sub c. It's called the support function of c. Support functions of convex sets are very interesting objects, and this is not the last time we will encounter a support function of a convex set in this course. Now, we have in fact already seen an example in which we minimize the max relative entropy over a set of models, and that's the conditional min entropy. Here's the definition of the conditional min entropy for a given density operator ρ. And that's obviously the same thing as the negative infimum of the max relative entropy of ρ with respect to Q, for Q ranging over the set C that's specified here, which is clearly closed and convex. In this case, the support function of C turns out to be a function that can be written explicitly. First, let's write this as a supremum over all density operators sigma by tensoring with the identity on X. The adjoint of the linear map you get by tensoring the identity operator to a given operator is the partial trace over the corresponding space, and so we have this equality. And the supremum is precisely the largest eigenvalue of the partial trace over X of Z. That is, if you want to make that inner product as large as possible, let sigma be entirely supported on the eigenspace corresponding to the largest eigenvalue of that operator. Now, if you think about the general dual problem that we just observed, you'll see that the conditional min entropy of X given Y for the state ρ is the log of the inner product of ρ with Z, maximized over all Z for which the largest eigenvalue of the partial trace is at most 1. You may have forgotten what the dual problem looked like, maybe because of that equation crawling around on the screen, but all I've done here is to take the logarithm of the objective function and then substituted our explicit expression for the function theta sub c. Now, the condition that the largest eigenvalue of a Hermitian operator is at most 1 is equivalent to saying that that operator is less than or equal to the identity with respect to the positive semi-definite ordering. And it's not too hard to see that the supremum might as well be limited to those Z for which the partial trace over X equals the identity. That's not obvious, but if you imagine that you have some Z for which the inequality holds, then you might see that there will always be some positive semi-definite operator that you can add to Z so that the inequality becomes an equality. And that can only make the objective function larger because ρ is positive semi-definite. And now we have an expression for the conditional min entropy that is exactly as before when we formulated the conditional min entropy as a semi-definite program. There's nothing at all unexpected about this, it's just a reality check and all is well, at least concerning the conditional min entropy. Another setting in which we consider the minimization of the max relative entropy over a convex set of models, which in this case will also be a convex set of states, is as follows. First, suppose we have a state ρ and a convex set of states C. And think about the infimum of the ordinary quantum relative entropy of ρ with respect to sigma, taken over all sigma in C. This is a quantity that in some sense measures the distance, or perhaps divergence is a better word, of ρ from the set C. For instance, the relative entropy of entanglement is a very well-known entanglement measure where we take the infimum over the set of all separable states, assuming of course that ρ is a state of a bipartite system. If ρ is separable, then this value is 0, and otherwise it's positive by Klein's inequality. It also satisfies other properties that make it a very interesting measure of entanglement. Anyway, we can do precisely the same thing with the max relative entropy rather than the ordinary relative entropy, and it's interesting what comes out. First, let's unwrap the definition. And observe that the inequality can be expressed as an equality if we introduce a positive semi-definite slack variable p. But now if you compare the trace of the two sides of that equality, you'll see that the slack variable p has to have trace equal to 2 to the lambda minus 1. So we can replace p by 2 to the lambda minus 1 times some density operator xi. Now divide through by 2 to the lambda and observe that we have sigma all by itself on the right-hand side, and it's free to range over the set C. So we might as well just say that the left-hand side is contained in C. And now we can visualize what's going on here. We have a convex set C contained in the set of all density operators, as well as a given density operator rho. We imagine that the quantity that we're talking about should tell us something about the distance or the divergence of rho from C. And it does in some sense. We can think about different choices of psi for which a convex combination of rho and psi yields a point in C, just like in the figure. And we try to minimize the value of lambda, for which the convex combination puts weight 2 to the negative lambda on rho. That means maximizing the weight placed on rho. You can take lambda equals 0 if and only if rho is contained in C, and otherwise lambda has to be positive and large when rho is somehow very far away from C. It's a natural concept, and in fact it predates the explicit identification and study of the max relative entropy. It's equivalent, up to a change of parameters, to a quantity that is called the generalized robustness of rho with respect to C, and it's also sometimes called the global robustness of rho with respect to C. There is a different notion of robustness where psi is constrained to lie within the set C, and this is sometimes simply called the robustness of rho with respect to C. But that's different from what we've obtained from the max relative entropy. Finally, and very briefly, let me mention that we can minimize in both coordinates simultaneously, and sometimes we want to do that, to consider a smooth variant of generalized robustness, for instance. It's actually not really any harder to set up a conic program to express this optimization, and here are the primal and dual problems we obtain. We could, by the way, have worked out just this one conic program from the start and gotten the 2 conic programs we already discussed in the lecture for free, but doing them one at a time has a higher pedagogical value, perhaps. Anyway, this is another good example that you may wish to work out for yourself for some practice in computing dual problems. That's all for this lecture. As always, please feel free to ask any questions if you have them.